That. All right. Hi, everybody. How's it going? Glad to hear that. So, a couple of housekeeping things before we get started. I want to point out that my agenda for the rest of the semester is up there on My Notre Dame. So this is the tentative plan for the rest of the semester. You guys were asking about the what is going on here? I've been asking. I think we're asking a little bit about the final exam before break. So I haven't finished. I've just been kind of sketching, but this is what I was kind of looking at, and I was thinking, okay, maybe the format I'll go on the final exam will be put 100 points worth of questions and grade out of 70. So the expectation would be not to finish everything, but whatever you finish, I'm going to score, and we'll just put the grade out of 70, and there's 100 points or whatever worth of things on there, because that's kind of reflecting the AP format here, where, if you get 70 out of the 108, it's still a 5. So that's kind of where I'm at right now. I don't have any real details beyond that, other than I was thinking a little bit about how to format this. That seems like maybe a good way of formatting things. What's up, Blake?
So, will you be giving us actual point values for each question then? Mm-hmm. So then we just do the math, figure out how to get the best way to get 70.
No, you can do more. You can do as much as you want. Okay. It's just going to be graded out of 70.
Oh, okay.
Right? Just like the AP exam is. It's not like you have to get to 70 points. You just do as many as you can, but if you get over 70, it's still a 5.
Yeah.
Right?
Yeah, no, okay, I get you.
I'm not saying that you have to pick that's a huge time waster. Do as much as you can.
Yeah.
You're just the expectation is that you probably won't finish, but that's okay. Because there's 100 points on there and you'll need to get to 70 of them. You know what I'm saying? If you do all of them and you're oh, I got 2/3 of the points on everything, it's well, you got 66 points. That's awesome. 66 out of 70, I'll take it. Right?
Yeah, I understand.
Whether you did, or I just did 70 perfectly, 70 points perfectly, oh, okay. This has been up there for a while. I don't know if you saw this, but this is the distribution for 5, 4, 3, 2, 1 when I looked it up, they didn't have the 2022 stuff posted, but this is the statistics for the score distributions. This is the test format, just 54 points from each. But that's up on the My Notre Dame page too. I guess maybe it hadn't all the way posted. I don't know how I peeked that up before, but it should be there now for you guys. So that's just a little bit about the final. As it gets a little bit closer and I get more done, I'll be able to give you a better clue as to how the specific formatting stuff works out. But that's kind of where I'm at in terms. I'm going to give you a lot of points and you'll need to finish or need to score it out of much less than is possible, kind of thing. Is that everybody's okay with that? That's not a ridiculous sounding format. Okay. Paul, what's up?
Are we going to get our lowest quiz for each round?
Mm-hmm. Yep. We're going to do questions to start here, too. So I think you guys had outstanding 4-1, 4-2, and 4-3 stuff. Blake, I guess we'll start with you, my man.
Could you do 4.4 number 65?
4.4 number 65. Okay. So these are just all L'Hopital problems. They're just like evaluate the limit. As far as the instructions go on this. Open this up real quick before I do something dumb. First things first is to check that we are in an indeterminate form, correct? So if I plug 0 in, cosine of x is, or cosine of 0 is 1, and 1 over 0 squared is infinity, right? So we have 1 to the infinity, which is one of our indeterminate forms. So this is an excellent candidate for L'Hopital. Now, we have to format this, though, in kind of a sneaky way, right? Because we can't just L'Hopital this because it's not written as a fraction. Everybody is okay with that? So remember what we want to do. This is like, I have like f of x to the g of x is kind of what's going on here. Everybody see that? So what I'm going to do is I want to write this then as, let me just double check real quick. Yeah, okay. So we do y equals, we'll do the natural log of both sides. I'll use my power property for logarithms to do that. And now I can rewrite this as one of two ways, right? Which one is usually the easier way to do this? We usually want to put the thing without the natural log in it as the denominator. Okay with that? So that's kind of our generic setup. In our case, our f of x is just cosine x, and our g of x is 1 over x squared. So let's do our limit as x approaches 0 from the right of the natural log of cosine x over, well, what's 1 over x squared? Just x squared, which is lovely. Okay. Let's L'Hopital that bad mama jamma then. So the denominator is easy. Oops, Mr. Kulik. Don't make mistakes. Take the limit with you. The numerator is a chain rule problem, right? What's the derivative of the outside going to be? 1 over the inside. And the derivative of the inside is negative sign. So this is the limit as x approaches 0 of negative tangent over 2x. If I check here, tangent of 0 is tangent is y over x, right? At the 0 degrees, that's the point 1, 0. So 0 over 1 is 0. And then 2 times 0 is 0. So we're still in indeterminate form. What do we need to do? Hit it again with L'Hopital. Derivative of negative tangent is negative secant squared. Very good. Derivative of 2x is just 2. That's looking pretty good because we're not going to be able to get something indeterminate out of this. What's secant of 0? How about this? What's cosine of 0? 1. What's the reciprocal of 1? 1. What's 1 squared?
1.
So this is negative 1/2. That's not our answer, though. Remember, because we got, this is the limit of the natural log of y. We want the limit as x approaches 0 of e then to the natural log y. That'll be the same thing as y, correct? So when we do that, I can use my limit of a composition function rule to do that. And we know that limit that we just did above is negative 1/2, so we just have e to the negative 1/2. And if you wanted to get fancy about it, you could write it as this. I don't know what the answer the back of the book has, but I'm good with either. Blake, happy?
Happy as I can be.
Okay, sure. I like that answer. Be like, okay, yep, that's how you do it. Who's out? What else do we guys got? Happy to do more. Blake?
Do you mind if you do number, 39?
39,
From
same
section.
same section? Sure. Let's see here. Oops. Okay. First things first, we need to check to make sure it's in the indeterminate form, right? Okay, cosine of 0 is 1. So 1 minus 1 is 0, plus 1/2 times 0 squared, 0 over 0 to the 4th, indeterminate form. So this looks like L'Hopital to me, and it looks like it's going to be a really obnoxious one. Why do I say that? I have a feeling we're going to have to do 4 L'Hopitals on it. That's what my instinct is going to tell me before I can get the 0 out of the denominator. So, which is like, ugh, all right, fine. But let's see. Derivative of cosine is negative sine. Derivative of 1 is 0. The derivative of 1/2 x squared is 1/2 times 2x. And the derivative of 4x, or x to the 4th, is 4x cubed. If I check again, let's see, I get sine of 0 is 0. And then 1/2 times 0 is 0 over 0, still indeterminate. Okay. Well, let's L'Hopital again. So derivative of negative sine is negative cosine. Excellent. And this was just x, right? Okay. L'Hopital this again. Or sorry, plug this in again. So cosine of 0 is 1. So I have negative 1 plus 1. That's 0 over 0. Ah! Okay. I think Mr. Kulik's right. I think we're going to have to do this 4 times. Derivative of negative cosine is positive sine. Plugging in 0, sine of 0 is 0 over 0 is still indeterminate. Okay. The derivative of sine is cosine. over regular old 24. That we can do. Cosine of 0 is 1 over 24. So many L'Hopital's. Just L'Hopital and L'Hopital and L'Hopital till I couldn't L'Hopital anymore.
Do you mind taking a look at 71, same section?
Sure. Blake, you're happy with what we did there?
Yep.
You just didn't L'Hopital enough?
I don't, like, I did it before the break and I'm looking at, but I didn't. I don't know. I might have been doing the wrong math.
Oh, okay. Fair enough. Fair enough. That happens. All right. 71 says, prove for any positive integer n. Prove that this limit is equal to infinity for any positive integer n. This shows that the exponential function approaches infinity faster than any power of x. And we had kind of mentioned this earlier, right? Way back in chapter 2, we talked about like how fast some of these functions grow, and the exponential is like kind of like your fastest growing one. So that we could like eyeball some of these limits without actually having to do things. This is what the proof would be. So here's what I would do. That's, if I plug in the infinity, I have infinity over infinity, right? That's indeterminate form. L'Hopital's. How many times am I going to have to do L'Hopital? N times, right? Now, the nice part about this is what's the derivative of e to the x each time? E to the x. Great. So what's going to be the derivative, the nth derivative of x to the n?
And x to the n minus n.
Because I'm going to have n times x to the n minus 1, and then I do it again, I'll have n times n minus 1 times x to the n minus 2. I'll do it again all the way down until I get x to the first. So the coefficient will be n times n minus 1 times n minus 2 times n minus 3 all the way down to 1, n factorial. And this is definitely then infinity.
What is that notation? It's n, and then what is that?
Factorial? So like 3 factorial means 3 times 2 times 1. So like n factorial is n times n minus 1 times n minus 2 all the way down to like times 2 times 1. Now, you didn't really have to write that. You could have put that in the same spot. It's fine. I just looking for compactness. Are you just looking at that going, that took so little time. I'm amazed that that looked like a terrible proof. And it's like L'Hopital, man. It's a wonderful thing. Now, being able to see what the nth derivative of x to the n was maybe not trivial, but, or that you needed to do L'Hopital n times there. Not trivial, but like, if you knew what to, if you saw what to do, it's like, oh, that's one of the quickest darn proofs I've ever done.
Explain me how you got n factorial again. I'm just like, wouldn't it be like x?
So I do the first derivative. I have that, right?
Yes.
I'll do the second derivative. Oops. Right? I'll do a third derivative. Right?
Oh.
I'll keep going. Eventually we get down to like that. And I do it one more time. Just n factorial. Because the x goes away.
I see what you're saying.
That's all we did. Just kept doing it. Lots of derivatives.
And derivatives.
Yeah, we did. That's the nth derivative. That's exactly right. You didn't think that one was going to be that quick, did you? It's like that has to be super involved. Yeah, I mean, it was involved, but like when you see what to do, it's like, oh, it's a 2 lines or whatever. Not bad. Shorter than most of the other L'Hopital problems we had done in this section. What else do you guys want to talk about? All right, Blake again.
Do you mind doing number 83 in the same section?
Sure. Let's see here. Okay. Evaluate this guy. So this is well, it should be pretty clear this is an indeterminate form problem, right? Since you're doing the log of a number bigger than 1, that's going to be a positive value. So times infinity minus infinity. So it's infinity minus infinity, right? So what was the trick for a subtraction problem? I forget even the trick. What was it? Let me go back and look real quick. Quotient. There it was. Differences. Okay. Oh, it was just a trig trick, hoping to make it work, huh? Okay. Let's try this then. Well, maybe I should, before I get going, be humble, Kulik. Okay. Yep. Let's make a substitution to create a fraction here. So I'm going to do that. So if I do that, x minus x squared, natural log of 1 over x. Well, let's write it this way also. That probably makes more sense to do it that way. So I have 1 over t plus 1 over t squared, the natural log of t plus 1. So if I make a common denominator, I have that. Everybody's okay? Now here's the sneaky part. What does, bless you, what does t go to as x approaches in the limit as x approaches infinity? Very good. Right? So let's write it this way. And we should be a little bit more technical than that, because it's positive infinity. 0 has to be from the right, I don't know if that's going to matter. I suspect it might with the logarithm there, because I know I can't do the log of 0 or the log of a negative. So I think that plus might end up mattering. So we have now the limit as t approaches positive 0 from the right of t plus the natural log of t plus 1 over t squared. So I have 0 plus the log of 1, which is 0, over 0 squared, indeterminate. The good news is I can L'Hopital this now. So the natural log, or the derivative of t is 1. The derivative of the natural log of t plus 1 is a chain rule. Derivative of the outside is 1 over the inside times the derivative of the inside, and then over the derivative of the bottom. Oops-a-daisy, what did Mr. Kulik do wrong? Forgot his limit. I'll be picky about that. I warned you guys. Okay. If I try this again, if we plug 0 in, I have I have 1 over, or I have something over 0, right? Or 2 over 0. Don't love that. Can we do any better? Here's what I would try. Is let's make a common denominator in the numerator where I have that complex fraction. So that's going to give me t plus 1 all over t plus 1 over 2t.
So why would you do that instead of L'Hopital?
Oh my gosh, guys. Look at this. It's like something's not working out. Why am I doing this rather than L'Hopitaling again? Because it's not in the indeterminate form. Because I have number over 0. That's not indeterminate.
Yep.
That's why I'm going through this hassle right now. Okay. So those guys cancel each other out. So I'm going to have then t over t plus 1 times 1 over 2t. And this, I like what's happening. Look, I got rid of the dividing by 0 piece. And now if I direct sub, I get 1/2.
So then could you infer and say that 1/2 for that, like that the limit of x, as x approaches infinity is 2 then?
No, I don't think we need to. I don't think we need to say that at all. I think we're done. I think that it's just 1/2 because we didn't. because this is strictly equal to the limit as t approaches this of, 1 over t plus 1 over t squared, right? This is strictly equal. So because I changed the boundary of my limit, I don't need to do anything else with this. You know what I mean?
Okay, yeah, I see what you're saying.
Because I evaluated something that's strictly equal to it. All I did was substitute, and I made all the proper substitutions. Right? Does that feel okay? Okay.
Yeah.
All right. Let's start 4-3 then. I think we've done enough for today. We can always do some more next time. So 4-3's should be a relatively straightforward section. It's just building off ideas that we've developed in 4-1 and 4-2. So we're going to start by this whole section is about how what the derivatives can tell us about the shape of our function. So we'll start off by talking about what the first derivative can tell us. And then we'll finish by talking about what the second derivative can tell us about the shape. Okay? When I say shape, I mean like the shape of the graph. So our first thing is the first derivative can tell us about whether we are increasing and decreasing, right? Wherever the first derivative is positive, we're increasing, or f is increasing there, and where it's negative, f is decreasing there, right? Let's prove this. This will tie together some tools that we've developed in kind of the previous sections. It'll be nice to kind of go back on. So we're going to just prove the first part of this because to do the second part, it's like the exact same thing. It's kind of once you've done the first part, the second part is fine. So we're going to let f prime of x be greater than 0 on, well, let's say let x1 and x2 be real numbers such that x1 is less than x2. And f prime of x is greater than 0 on the interval from x1 to x2. That's kind of the hypothesis of our statement we're trying to prove, right? If f prime of x is greater than 0 on an interval, so we define the endpoints for the interval as just two real numbers, one smaller than the other, and we just said, okay, the derivative is positive on that interval. What we need to show is that f is increasing on that interval. All right. Since the derivative is positive on that interval, we know that f prime, or well, let's say f is differentiable on that interval. And what does differentiability give me? Excellent. Does the reverse work? No. What's our counterexample for continuity not giving us differentiability? Absolute value function, sharp corner, exactly. Perfect. Excellent job, guys. All right, so we have continuous on an interval. What can we use? mean value theorem. Oh, I should probably say more than this. We know there exists C on the interval here such that f of x2 minus f of x1 is equal to f prime of C times x2 minus x1. That's one of the forms of the mean value theorem, right? What can I say about f prime of C? Where does C come? Right, excellent. C comes from the interval from x1 to x2, and I know the derivative is always positive there. What can I say about x2 minus x1? If x1 is smaller than x2, that's got to be positive then, right? Big minus little better be positive, right? I know, it's early. So what can I say then? That this f of x2 minus f of x1 has to be greater than 0. So if I add f of x1 to both sides, I can say this, right? So if I have that x1 is less than x2, but f of x2 is bigger than f of x1, what does that look like? This, right? What's that tell me? And we're increasing. And we're done. Okay. Let's take this idea of this increasing decreasing test and do a specific numeric example. So example 1 says find where the function f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5 is increasing and where it is decreasing. First thing we should observe is that function continuous? Yes. Great. How do I know? It's a polynomial. Perfect. Okay. So if it's continuous, where's the only place that it can change from increasing and to decreasing, or decreasing to increasing? At a minimum or a maximum, right? Those are the only places that a continuous function can change from increasing to decreasing or decreasing to increasing. What do you know about that? Is equal to 0, right? At a max or a min, that was a 4-1 concept, right? Or 4-2, I don't remember which one. Maybe some of both. I think those two sections were really closely related. So what I'm going to do, is I'm going to just take my derivative. Now, hold on a second. And I'm going to look for the critical values, right? Because maxes and mins on a function don't always have to occur when the derivative is 0. The derivative could also be undefined. Now, let's look at our derivative here. What kind of function is it? Polynomial. So it's continuous. Can that ever be, are continuous things ever undefined? No. So all we're worried about is where the derivative is 0. Sorry, I needed to say that before we dove in, that we need to at least give that some lip service as to why I'm only concerned about where the derivative is 0, because I know it can't be undefined anywhere. Or you could just say from the jump, since this is continuous everywhere, I know it's differentiable everywhere. Or nope, can't say that. My bad. Continuity doesn't give differentiability.
Right, but like, there's no absolute value.
No, I understand, but you can't say just because it's continuous. I don't want to go down that road. But yes, yeah, you definitely know that the derivative of a polynomial is another polynomial. So that's going to be continuous everywhere. Yeah. All right. How do I solve something like this? Perfectly within your abilities to do this without a calculator.
Move out the 12x and factor.
Great. Factor out a 12x. That's the greatest common factor. And then what? Okay, the quadratic that remains we can factor. How does that factor? Great. So what are the solutions then? 0, 2, and -1. Excellent. So these are my critical values using the parlance of last couple of sections. So what I'm going to do now is I'm going to make like a little interval here. So the values I'm concerned with are -1, 0, and 2. Okay with that? Now I'm going to pick a test value in each of these 4 intervals and evaluate the first derivative there, and that'll tell me whether on that interval the function is increasing, decreasing, or constant. So from the interval from -∞, maybe I'll write that over here, to -1, let's pick -2. Cool with that? Now to evaluate this, I'm going to use the factored version. So when I plug in -2 for x, I get a negative times a negative times a negative. Everybody agree? So that is negative. Everybody cool?
So,
Do I actually care what it evaluates out to? No. Yes, Blake.
so we can use, so f, would that be f?
Oh, yes, sorry.
-2 or
Yes. F prime is -2. Yes, 100%. Okay. Between -1 and 0, I'll pick -1/2. We'll do the same thing. I get negative times positive. Everybody agree? So that should be positive. Okay. Between 0 and 2, I'll pick 1. When I plug 1 in, I get positive times negative times positive. So that's negative.
Wouldn't it be positive times negative times 0?
Plugging in +1, not -1.
What is it, x plus?
Yeah, 1 plus 1 is 2, not 0.
Oh, sorry.
It's okay, man. It's okay. It's going to be one of those days. Everybody has them. It is okay. It's okay. And then for last interval, I'll pick 3, something between 2 and +∞. When I plug that in, I get positive times positive times positive. That's positive. So this interval and this interval are decreasing. And then this interval and this interval are increasing that feel okay to you guys? Right? No big deal. The calculus is pretty easy. The algebra is pretty easy. Not a big deal. Next concept is called the first derivative test. This says that suppose c is a critical number of a continuous function f, and then we have three parts. If f prime changes from positive to negative at c, then f has a local maximum at c, which makes sense, right? If we go from increasing to decreasing, that's going to be at a maximum there, right? Increasing to decreasing. If you just think about the picture. Part B says if f prime changes from negative to positive at c, so decreasing to increasing, we should have a local minimum at c. And then the part C says if f prime does not change sign at c, so it goes from like decreasing to decreasing, we don't have any extrema there, or increasing to increasing, again, we don't have any extrema there.
So we're just determining what C is.
Yeah, exactly right. That's all we're doing with the first derivative test, is deciding whether that value for C is a maximum or minimum or nothing. Cool? So find the local mins and max for the function f in the previous example. Oh, okay. Well, let's look here. So at -1, we went from decreasing to increasing. That's a minimum. For 0, we went from increasing to decreasing. That's a maximum. For 2, we go from decreasing to increasing. That's a minimum. That's it. That's all we're doing. Isn't it lovely when we can take like the work we've already done and just like repackage it and find out more information about something? I love it when that happens. It's like I'm getting something for nothing.
Just to make sure that I got this, I got a handle on this. So the first derivative test can't work if you have like a what do we call that? Parabola.
You need a continuous function.
Okay.
If it's not continuous, you can't get
Yeah, then you can't do that.
right. What you could do is you could separate it out into the continuous pieces and then evaluate each piece of its domain separately
Yeah.
and deal with it that way, and that would be okay. But you need continuity here to do this. All right, so let's look at another example. First thing we need to check is continuous. Okay, so is g of x continuous? Yes, good. Why? It's not trig. This is the sum of two different kinds of functions. It's a polynomial, which is continuous, plus a sine function, which is continuous. Continuous plus continuous is continuous. Yeah, super continuous. Again, just wanting to like walk through the whys, because those are important, right? Now, would I ask you to justify it on the thing? Depends on the directions, but like if it's not continuous and you start using the wrong stuff, like that's a big problem, right? Okay. So let's go ahead and find the derivative. Now notice, what can we say about this derivative? It's continuous also, for the same reasons, right? Polynomial plus a cosine function, continuous plus continuous is continuous. So all I have to worry about then is where the derivative is equal to 0. There are no places where the derivative fails to exist. So to solve this for x, I'm going to subtract 1 and divide by 2. And then we'll do the cosine inverse to both sides. And then here's your trig quiz. What values or what angles is cosine equal to -1/2? What quadrants are we going to be in? Give me them. Oh my God, no! 2 and 3. Cosine is the x. The x is negative in quadrants 2 and 3.
Oh shoot. Right.
It's okay, guys. It's okay.
Well, I discussed the two that you didn't.
Tegan looked smart and he's like, I didn't know. I just knew that if he said no to those, I guess the other two. Okay, so in quadrants 2 and 3, what angles are we looking for? It's 2 pi over 3 and 4 pi over 3. So it's 120 and then 240. Where you have a 60-degree angle with the x-axis. Again, the AP's expectation is that you are able to do these unit circle things without a unit circle. Or a calculator even. Like, would not be an unfair thing to pop up onto a no calculator question. I know. But we did it once. You knew it at one point. You knew it really well at one point. And it's faded. That's okay. I'm just reminding you that, like, this, let's make a little Quizlet and we can just bang out some memorization and get this sharpened back up a little bit. Okay. So I'll make my interval here. So I have 0 and 2 pi are the ends. And then 2 pi over 3 and 4 pi over 3. What value do you want to pick? What would be a smart value to pick here between 0 and 2 pi? Pi over 4. Or I'm sorry, pi over 2, excuse me.
Oh, okay, that's great.
Yeah. What's cosine of pi over 2? Okay, so 1 plus 2 times 0 is positive. How about between 2 pi and 4 pi? Yeah, that's what I would pick. What's the value of, or what's cosine of pi? So 1 plus 2 times -1 is negative. And then between 4 pi and 2 pi, I'd pick 3 pi over 2. Yep. And what's cosine of 3 pi over 2? 0. So again, that gives us a positive. So what can we say here? 2 pi over 3 goes from increasing to decreasing. So that is a And then 4 pi over 3 goes from decreasing to increasing. It's a local minimum. That's it. Not bad, right? Algebra's pretty easy. The calculus is pretty easy. Remembering your trig stuff, maybe not that easy, but that's okay. We were good at it before. It'll come back. All right. Let's now talk about what the second derivative can tell us. Before we can start talking about what the second derivative can tell us, we need to define something. So we say if a graph of f lies above all of its tangents on an interval I, then it is called concave up on I. And if the graph lies below all of its tangents on I, it is called concave down on I. Really, the way I think about this is, like if I'm dumping water on top of this, if it runs off, that's concave down. If I'm pouring water in here and it like pools at the bottom, that's concave up. That's kind of the way that I think about it visually, because most often I just want to be able to look at the picture. So this section here is concave, down. This section here is concave down. This section here is concave down. In all those cases, water would like run off, it wouldn't catch. And then these other sections are concave up. So just giving you a visual of like what this looks like on the graph. As you might have guessed, the end result for this section is going to be to like, here's a function, sketch its graph. So just like for the first derivative, we'll start with the concavity test, just like we had our increasing decreasing test. If the second derivative is positive on some interval, the graph is concave up on that interval. Or the graph of f, I should say, is concave up on that interval. If the second derivative of f is negative on that interval, then the graph is concave down on that interval. Just like the first, or just like increasing decreasing test was, right? Same idea. Just using the second derivative instead of the first derivative. Okay. Definition. Yeah. We say a point P on the curve f of x is called an inflection point if f is continuous there and the curve changes from concave up to concave down or from concave down to concave up. So if we go back to our picture here, that's an inflection point. That's an inflection point. That's an inflection point. This one, though, E is not an inflection point because we're just going concave up, concave up. And then P is also an inflection point. Everybody cool with that? So very similar to like a max or a min, right? Where maxes and mins are changing concavity, or changing increasing to decreasing. Inflection points are changing concavity from concave up to concave down or vice versa. Okay. All right. Sketch a possible graph for the function f that satisfies the following conditions. 1, f of x, or f prime of x is greater than 0 on the interval from negative infinity to 1. What's that telling us? We're increasing from negative infinity to 1. And f prime of x is negative from 1 to positive infinity. That's telling us where the graph is decreasing. Condition 2. The f double prime of x is greater than 0 from negative infinity to negative 2. So that's where we are, concave up, and also from 2 to positive infinity, we're concave up. And the second derivative is negative on the interval from negative 2 to positive 2. That must be where we're concave down. The third condition says the limit as x approaches negative infinity of f of x is equal to negative 2. That's our left end behavior. That's what the left arrow on my graph is going to be doing. And the limit as x approaches positive infinity of f of x is equal to 0. That's my right end behavior. That will be what the arrow at the right side of my graph is going to be doing. All right. Let's kind of start sketching something out here. Oops. So there's negative 2 down there. So I cared about negative 2, 1, and 2 on the x-axis, and then just about the value negative 2 and 0 on the y-axis. I'll go ahead and draw in like a dashed line for me for my end behaviors. I don't know if these will be asymptotes or not. Sometimes it's tough to tell whether the graph will have to cross or not to draw it. But if you remember back in chapter 2, we just defined a horizontal asymptote if the limit is blah, 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 blah. So technically, these are asymptotes by that definition or whatever. All right, so let's start sketching then. So from negative infinity to 1, we're increasing. So I need to do that. The left end needs to be following negative 2. So I need to be at least kind of starting like that. Oh, and we need to be concave up on that section, which is what I've already started drawing naturally, right? Which is nice. So we'll go all the way up. Oops. To here. And we'll put our inflection point, because I know at that point we're going to start changing concavity. So instead of having it being like a basin to catch water, I'm going to have it like a dome. Now, but I'm still increasing, right? So all the way to 1. We're still increasing. We're still concave up. Now, let's go and check and see what we have here. So now we need to start being decreasing. And we need to be still concave. I'm still concave down for a little bit more, right? Let's do it like that so it overlaps a little bit. And then after this, we're back to concave up again. Does that feel okay with everybody? So we're going to go down to here. And this, I guess, we can tell that's a local maximum, right? Since we've changed from increasing to decreasing there. There's my inflection point. We're going to continue decreasing now, but we're going to change to concave up. Oops. But we're following not negative 2, but 0. Now, notice that this is a sketch, right? Was there anything specific about the y coordinates that I used? The only places that I'd be worried about were my end behaviors, because that's the only thing that I knew about. right? That's the only thing I knew anything about the y-coordinate on. So I almost I didn't even bother with any kind of y scale on this. So your pictures will vary a little bit. That's okay. They just have to meet the attributes. Does that feel okay? That's usually the hardest thing, is getting a picture drawn. Okay. Second derivative test says suppose f double prime is continuous near C. Notice that you don't need f double prime to be continuous everywhere, just near some point C. So if the first derivative is 0 and the second derivative is positive at C, then that means C is a local minimum. And if the first derivative is 0 and the second derivative is negative, then there's a local maximum at C. What's the problem here, though? There's a couple of key points to turn out. So what happens if the second derivative is 0? It's inconclusive. We don't know whether it's a max or a min. What else could have happened? If it doesn't exist at C, or if the second derivative doesn't exist at C. In either case, what should we use? And in general, which one would Mr. Kulik be using? First derivative test, because I don't want to have to monkey around with like, oh no, I did all this work and then it didn't work. Right? Now, the second derivative test is quicker because there's less stuff to evaluate, but like, I don't think it's worth every once in a while running into like something that doesn't work. Paul, what's up? Certainly.
Do you like know if it doesn't work? Will you get like a?
Well, when we evaluate the second derivative at C, you'll get one of these outputs. Okay. And it's like, oh, that doesn't fit any of the criteria for my test. What do I do with that? You have to go back and do the first derivative test, which isn't like a ton more work in all reality. But like to do the first derivative test, you have to evaluate on each side of C. Mm-hmm. Here, you just have to evaluate just the second derivative at C, instead of having to do a test point on either side of it.
Yeah.
Right? So it's not like it's a ton more work to do the first derivative test. Like, I don't know. But anyways. All right. Let's do this. Discuss the curve y equals x to the fourth minus 4x cubed with respect to concavity, points of inflection, local max and min, and then use that information to sketch the curve. Okay. First thing to look at, what kind of function are we dealing with? Polynomial, so it's continuous. So its derivatives are also going to be polynomials and therefore continuous, right? So let's go ahead and write these. I'm going to use f instead of y here because it makes the rest of the notation that I like to use elsewhere a little bit more convenient. So there's my first derivative. There's my second derivative. Since these are both continuous, all I need to worry about is where they're equal to 0, correct? So to solve these, I'm going to factor. So for the first one, what are my solutions here? 0 and 3. Excellent. And for the second one, my solutions are 0 and 2. So we'll set up our little intervals here. So we'll pick some test values now and plug them in. So I'll pick -1. When I plug -1 into the first part, anything I plug into that's going to be positive, right? Because it's squared. So I just have positive times negative, so that's negative. I'll plug 1 in. Again, I have positive times negative, so negative. Then I'll plug 4 in. It's positive times positive, so that's positive. So this is nothing. But if we go from decreasing to increasing, that's a local min. We'll do the same thing over here, except with the second derivative. So I'll pick -1, +1, and 3. And again, plugging into the same spot. When I plug -1 in, I get negative times negative, so that's positive. When I plug +1 in, that's positive times negative, so that's negative. When I plug 3 in, that's positive times positive, so that's positive. So each of these are inflection points. Oh boy, what happened here? OneNote, you're just drifting on me. So let's make a little summary here. So we are, well, let's do decreasing first. We are decreasing from -infinity to 0, and then from 0 to 3. Notice that I didn't do that all as one interval. Why not? Because the derivative is 0 at x equals 0, so it can't be decreasing at that one spot. So I had to do it as 2 separate intervals. Everybody see that? I couldn't just do that as one interval because at 0, the derivative is 0. So it's not technically decreasing the entire way. Remember, the definition for decreasing was that the first derivative needs to be less than 0. That's why it had to be separated into 2 pieces, even though it's like, why? That's why. And then we have a local min at x equals 3. We are concave up from -infinity to 0, and then again from 2 to +infinity. We are concave down from 0 to 2, and we have inflection points at x equals 0 and x equals 2. So there's my little summary, right? I think that discusses all the things they asked us to. Then they ask us to sketch the curve. Okay, well, let's do that too. The values that I'm going to care about on my x-axis are going to be 0, 3, and 2. All right. Everybody's cool with that? Okay. So I know I'm going to be decreasing from -infinity to 0, and then from 0 to 3. Okay. Now over that same space, we're going to be concave up there and there. Everybody's cool with that? So I'm going to be decreasing or concave up till we get to 0. Then we change the concave down to 2. And then, oops, what am I doing? I have to start increasing there. Sorry. So concave up to 0. Wait, okay. Did I copy something down wrong, John?
I thought it was just decreasing until 3 and then it switches.
Oh, yes. Okay, sorry. Yep. Okay. So concave down. So, and we're staying concave down to 2. And then we have another inflection point. And we switch back to concave up, still decreasing to 3. Okay, and there's my local min. Oops. And then here we're going to be now concave up and increasing. Oops, that concave up color was supposed to be the green. So we're just going to be like, so something like that. What do you guys think? If I wanted this to be more specific, like if I wanted the coordinates for these, what would I do? Plug it into f, right? This would be the point 0, f of 0. This would be the point 2, comma, f of 2. So the point 3, comma, f of 3, right? Whatever those were, you could make it a little bit more specific and then give yourself some landmarks to connect. You could plot those points first, which gives maybe at the beginning, like while you're still kind of getting the hang of this, it makes it a little bit easier if you have like specific dots to connect, and then you just have to like make sure you're drawing the line in between them the correct way. But that's the idea. I had one more example there, but it's the same thing, so it's not a big deal. This is the 4-3 homework set. This is also up on My Notre Dame. I'm going to add this one into the other 3 problems, or the other 3 homework sections that are due Sunday. Everything else this week is going to go into the following weeks. Sound good?
I'll see you in like 3 weeks.
Oh, yeah. Good luck with all your medicals. You're welcome.